You're driving 70 miles per hour. That means your car, a 3,800-pound machine made of steel, glass, and plastic, is moving at 103 feet per second. Per second. In the time it takes you to read this sentence, you've traveled the length of a football field, and the only thing standing between that momentum and the stopped minivan ahead of you is 4 patches of friction material, each roughly the size of your hand, pressed against 4 spinning metal discs by a hydraulic system powered by your foot. That's it. That's what stops your car. Friction pads squeezing metal discs. The entire braking system, one of the most safety-critical systems on any vehicle, is based on the same principle as rubbing your hands together to create heat. You're converting the kinetic energy of a 2-ton object moving at highway speed into thermal energy, heat, through friction. And you're doing it in roughly 150 to 200 feet if everything works correctly. Most people never think about their brakes until something goes wrong. A squeal, a grinding noise, a pulsation in the pedal, a longer than normal stopping distance that makes your chest tighten, and by the time those symptoms appear, you're already past the point where a simple pad replacement would have fixed everything. Now you need rotors, maybe calipers, maybe a full brake job that costs 3 times what it would have cost if you'd paid attention 6 months earlier. Brakes are the most important safety system on your car, more important than airbags, because airbags respond to crashes that brakes are supposed to prevent. Understanding how they work, when they need service, and what the warning signs mean isn't just mechanical knowledge, it's survival knowledge. Before we get into the hardware, you need to understand what's physically happening when you brake, because the physics explains everything about how brakes are designed, why they wear out, and what the limits are. A moving car has kinetic energy, the energy of motion. The amount of kinetic energy is determined by the car's mass and the square of its speed. That square part is critical. Doubling your speed doesn't double your kinetic energy, it quadruples it. Going from 30 miles per hour to 60 miles per hour means your car has 4 times the kinetic energy. This is why stopping distance from 60 miles per hour is roughly 4 times the stopping distance from 30 miles per hour, not twice. Speed kills stopping distance exponentially, not linearly. When you press the brake pedal, friction material is pressed against a spinning metal surface. The friction between the 2 surfaces converts the car's kinetic energy into heat. The metal surface and the friction material both absorb this heat. The car slows down because its kinetic energy is being transformed into thermal energy. Literally, the brakes get hot and the car gets slower. That's the trade. Motion becomes heat. The amount of heat generated is enormous. A single hard stop from highway speed can raise brake rotor temperatures to 500 to 600 degrees Fahrenheit or higher. Repeated hard stops, like descending a mountain pass, can push temperatures above 900 to 1,000 degrees. At these temperatures, the rotor glows visibly in the dark. This is normal for the system. Brakes are designed to handle this heat. But exceeding the design limits is where brake fade, warping, and failure begin. Disc brakes are used on the front axle of virtually every modern car and on all 4 corners of most vehicles built in the last 15 to 20 years. They're the dominant braking technology because they offer the best combination of stopping power, heat dissipation, consistency, and serviceability. A disc brake system has 4 main components per wheel. The rotor, a flat, circular metal disc, typically cast iron, sometimes carbon ceramic on high-performance vehicles, that's bolted to the wheel hub and spins with the wheel. The rotor is the surface that the friction material presses against. On most cars, the rotor is vented. It has internal cooling fins between the 2 braking surfaces that allow air to flow through the rotor, helping dissipate heat. Solid, non-vented rotors are used on some rare applications where heat generation is lower. The rotor's diameter and thickness determine its thermal mass, how much heat it can absorb before reaching problematic temperatures. Larger rotors absorb more heat and resist fade better. This is why performance cars and heavy vehicles have larger brake rotors than economy cars. A sports car might have 14-inch front rotors. A standard sedan might have 11-inch front rotors. A heavy-duty truck might have 15-inch or larger rotors. Size directly correlates with braking capacity. The brake pads, 2 pads per caliper, one on each side of the rotor, that contain the friction material bonded to a metal backing plate. When the brakes are applied, the pads are squeezed against the rotor, creating the friction that converts kinetic energy to heat. Brake pads are the primary wear item in the braking system. They gradually thin with use as the friction material is consumed. Most pads start at 10 to 12 millimeters of thickness and are considered worn at 3 to 4 millimeters. Below 2 millimeter, you're at risk of metal-to-metal contact, where the backing plate grinds directly against the rotor, destroying both components and dramatically reducing stopping ability. Brake pad compounds vary. Organic pads, also called NAO, non-asbestos organic, are the quietest and gentlest on rotors, but wear faster and have lower performance limits. They're standard on most economy and mid-size vehicles. Semi-metallic pads contain metal fibers that improve heat dissipation and performance under hard use, but are noisier and create more rotor wear. They're common on trucks and performance vehicles. Ceramic pads use ceramic fibers and compounds that offer quiet operation, low dust, and good performance across a wide temperature range. They're a popular upgrade for daily drivers who want less brake dust on their wheels. The caliper. The caliper straddles the rotor and houses the brake pads and pistons. When you press the brake pedal, hydraulic pressure pushes the piston, or pistons, inside the caliper outward, pressing the brake pads against the rotor. Most passenger cars use a single piston floating caliper. One piston pushes the inner pad against the rotor, and the caliper slides on pins to pull the outer pad against the rotor's other face. Performance vehicles often use multi-piston fixed calipers, 2, 4, or 6 pistons on each side of the rotor that apply pressure more evenly across the pad's surface, improving profing force and feel. Brake lines and fluid. Hydraulic brake fluid transmits the force from the brake pedal to the calipers. When you press the pedal, a master cylinder converts your foot's mechanical force into hydraulic pressure, which travels through metal and rubber brake lines to each caliper. The fluid must be incompressible, meaning it transmits force without absorbing it, and must resist boiling at high temperatures. When brake fluid boils, it creates gas bubbles that are compressible, resulting in a spongy pedal and dramatically reduced braking force. This is called vapor lock, and it's one of the most dangerous brake failures because it happens suddenly during hard braking when you need the brakes most. Brake fluid absorbs moisture from the atmosphere over time through the rubber components in the system. As moisture content increases, the fluid's boiling point decreases, making vapor lock more likely. This is why brake fluid should be replaced every 2 to 3 years regardless of mileage. It's a time-based service, not a mileage-based service. Most people never change their brake fluid, which is why 5-year-old brake fluid with a significantly degraded boiling point is one of the most common hidden safety issues on otherwise well-maintained vehicles. A brake fluid flush costs $80 to $150 and takes about 30 minutes. It's one of the cheapest and most overlooked safety maintenance items on any car. When you install new brake pads and rotors, there's a critical break-in procedure called bedding that most people skip because nobody tells them about it. Bedding is the process of transferring a thin, even layer of pad material onto the rotor surface. This transfer layer is what creates optimal friction. The pad material grips against its own transferred material on the rotor rather than against bare metal. A properly bedded brake setup provides stronger, more consistent, and quieter braking than one that was never bedded. The typical bedding procedure involves a series of moderate stops, decelerating from 35 to 40 miles per hour to about 10 miles per hour, 6 to 10 times in succession, without coming to a complete stop. Then a series of harder stops from 50 to 60 miles per hour. Then allowing the brakes to cool completely by driving at moderate speed without braking for several minutes. Skipping the bedding process can result in uneven pad deposit on the rotor, which causes vibration and pulsation, and reduced braking performance during the break-in period. If you've ever had new brakes installed and noticed they felt weak or inconsistent for the first few hundred miles, inadequate bedding was likely the cause. Most quality brake pad manufacturers include bedding instructions with their products. Follow them. 5 minutes of controlled stops creates a brake setup that performs better for the next 30,000 miles. Drum brakes were the standard before disc brakes became dominant, and they're still used on the rear axle of some economy vehicles and on the parking brake mechanism of many cars. Instead of a flat disc and caliper, a drum brake uses a hollow cylindrical drum that rotates with the wheel and a set of curved brake shoes inside the drum that expand outward against the drum's inner surface when the brakes are applied. The shoe expansion is actuated by a wheel cylinder, a small hydraulic cylinder inside the drum that pushes the shoes apart when brake pressure is applied. Springs retract the shoes when the brakes are released. Drum brakes have some advantages. They're cheaper to manufacture. They generate high braking force relative to their size, due to the self-energizing effect where the drum's rotation helps pull the shoe into tighter contact, and they're effective as parking brakes because the mechanical linkage can hold the shoes against the drum indefinitely without hydraulic pressure. But their disadvantages are significant for modern performance expectations. Drums dissipate heat poorly. The enclosed design traps heat inside the drum, leading to faster brake fade during repeated hard stops. They're more complex to service. Adjusting, inspecting, and replacing drum brake components requires more labor and expertise than disc brakes. They're more susceptible to water and contamination. Water can pool inside the drum and temporarily reduce braking force, and they're less consistent. Braking force can vary as the drum heats up and expands, changing the clearance between the drum and shoes. For these reasons, disc brakes have replaced drums on the front axle of all modern vehicles and on all four corners of most vehicles. Where drums survive: the rear axle of some base model economy cars. They're adequate for the light braking duties the rear axle handles. The front brakes do 60 to 80% of the stopping work due to forward weight transfer during braking, so the rear brakes can be simpler without significantly affecting overall performance. Anti-lock braking system, ABS, has been mandatory on all new cars in the U.S. since 2013, though it's been standard on most vehicles for much longer. It's one of the most important safety technologies ever developed, and understanding what it does helps you use it correctly. When you brake hard, the tires can lock up, stop spinning while the car is still moving. A locked tire slides across the pavement rather than rolling, and a sliding tire has less grip than a rolling one. Locked tires also can't steer. Once the front tires are locked, turning the steering wheel does nothing. The car slides straight regardless of where you point the wheels. This is why panicked, locked brake stops often end in collisions. The driver locks the brakes, tries to steer around the obstacle, and the car goes straight into it. ABS prevents this. Wheel speed sensors at each corner monitor the rotation speed of each wheel. When the ABS controller detects that a wheel is about to lock, its speed is dropping much faster than the other wheels. It rapidly releases and reapplies brake pressure to that specific wheel, many times per second. This modulation keeps the wheel right at the edge of locking without going over, maximizing braking force while maintaining steering control. The pulsation you feel in the brake pedal during an ABS activation is the system working. It feels unusual. A rapid vibration or chattering through the pedal, and sometimes an audible buzzing or grinding sound from the ABS pump. Many drivers experiencing this for the first time think something is wrong and lift off the brake pedal. This is exactly the wrong response. When ABS activates, you should maintain firm, steady pressure on the brake pedal and steer around the obstacle if possible. The system is doing its job. Let it work. ABS doesn't necessarily shorten your stopping distance on dry pavement. A skilled driver who can threshold brake, apply maximum pressure just below the lockup point, might stop slightly shorter than ABS. But ABS maintains steering control during emergency braking, which is often more important than raw stopping distance. Being able to steer around an obstacle while braking hard has prevented countless collisions that would have occurred with locked wheels. Modern ABS systems are integrated with other safety technologies: electronic stability control, ESC, traction control, and electronic brake force distribution, that work together to keep the car stable and controllable in a wide range of situations. These systems share the same wheel speed sensors and hydraulic control module, creating a comprehensive stability management platform that operates invisibly in the background of every drive. Brake fade is the reduction in braking effectiveness that occurs when the braking system gets too hot. There are two types. Pad fade. When brake pads get excessively hot, the friction material can undergo a process called outgassing. The binders and resins in the pad compound release gases that form a thin layer between the pad and the rotor. This gas layer acts as a lubricant, reducing friction and braking force. The pedal still feels firm, you're still generating hydraulic pressure, but the car isn't slowing down as effectively. This is the most common type of fade and the most dangerous because it can feel like everything is working normally except the car isn't stopping. Fluid fade. When brake fluid reaches its boiling point from heat conducted through the caliper and pads, it boils, creating gas bubbles in the hydraulic lines. Gas is compressible, so the brake pedal becomes soft or spongy as you're compressing gas instead of transmitting force to the calipers. In severe cases, the pedal can go to the floor with minimal braking effect. This is more immediately alarming than pad fade because the pedal feels obviously wrong. Brake fade is most likely during prolonged or repeated hard braking, descending a long mountain grade, track driving, or aggressive driving in hilly terrain. The solution on a mountain road is engine braking, downshifting to let the engine's compression resistance slow the car, reducing the demand on the brakes. The solution for track driving is upgraded brake pads with higher temperature ratings and high-performance brake fluid with a higher boiling point. If you experience brake fade on the road, don't panic. Reduce speed using engine braking. Apply the brakes intermittently rather than holding them. This allows some cooling between applications. Find a safe place to stop and let the brakes cool before continuing. If the pedal is spongy, fluid fade, the condition will improve as the fluid cools below its boiling point and the gas bubbles recondense into liquid. Brake noise is one of the most common complaints drivers have, and understanding the causes helps you distinguish between normal noises and warning signs. Squeal on light braking. A high-pitched squeal during light braking, particularly in the morning or after the car has sat overnight, is usually caused by a thin layer of surface rust on the rotors. Moisture from overnight condensation or rain creates a light rust film on the bare metal rotor surface. When you first apply the brakes, the pads scrape this rust off, creating a brief squeal that goes away after a few brake applications. This is completely normal and not a sign of any problem. Persistent squeal. A squeal that continues throughout driving can be caused by the pad compound vibrating against the rotor at a specific frequency. Essentially, the brake is making music, and the frequency happens to fall in the audible range. Some pad compounds are more prone to this than others. Ceramic pads are generally the quietest. Semi-metallic pads are the noisiest. Brake pad shims. Thin metal or rubber layers between the pad and the caliper piston dampen these vibrations. If shims are missing, damaged, or improperly installed, squealing can result. Glazing is another cause of persistent squeal. If brake pads are overheated or subjected to prolonged light braking, the friction surface can develop a hard, shiny glaze that reduces friction and generates noise. Glazed pads can sometimes be resurfaced by performing several moderate stops from speed to wear off the glazed layer. Severely glazed pads should be replaced. The wear indicator squeal. Most modern brake pads include a metal wear indicator, a small tab of spring steel attached to the pad that contacts the rotor when the pad is worn to its minimum safe thickness. This metal-on-metal contact creates a loud, persistent squeal specifically designed to be annoying enough to get your attention. This is a warning. Your pads are worn and need replacement soon. The squeal is the pad's way of saying, "I'm almost gone." If you hear this sound, schedule a brake inspection within the next week or two. Grinding. A grinding noise during braking is a serious warning. It means the pad's friction material is completely gone and the metal backing plate is grinding directly against the rotor. This is dangerous. Your braking capacity is severely reduced and the grinding is rapidly destroying the rotor surface. What would have been a $200 pad replacement is now a $500 to $800 pad and rotor replacement because the rotor is damaged beyond safe use. If your brakes are grinding, get them inspected and repaired immediately. Do not continue driving with metal-on-metal brakes. How long do brakes last is one of the most common questions, and the honest answer is, it depends on everything. Brake pad life varies enormously based on driving style, vehicle weight, driving environment, and pad compound. A set of brake pads might last 25,000 miles for an aggressive driver in hilly terrain or 70,000 miles for a gentle highway commuter in flat country. The average is roughly 30,000 to 50,000 miles for front pads and 40,000 to 60,000 miles for rear pads. But these are broad averages with wide variance. Rather than relying on mileage, use these indicators to determine when replacement is needed. Pad thickness. Have your pads inspected visually during regular service. Many shops include this in an oil change inspection. New pads are 10 to 12 millimeters thick. Replace at 3 to 4 millimeters. Below 2 millimeters is urgent. Wear indicator noise. The squealing tab described above. If you hear it, schedule service promptly. Brake pedal feel. If the pedal feels different, longer travel, less firm, pulsating, something has changed. A pulsating pedal typically indicates warped rotors. A soft pedal may indicate air in the lines or worn pads. A pedal that sinks slowly while held at a stop can indicate a master cylinder leak. Any change in pedal feel warrants inspection. Stopping distance. If you notice the car taking longer to stop than it used to, don't wait for confirmation. Have the brakes checked. When you press the brake pedal, the car's weight shifts forward. This is basic physics. The deceleration force causes the car's mass to load onto the front axle and unload from the rear. You can feel this as the nose dives down and the rear this slightly during hard braking. This forward weight transfer means the front tires carry significantly more of the vehicle's weight during braking, and since grip is proportional to the weight on the tire, the front tires have more available grip. This is why the front brakes do 60 to 80% of the total braking work on most vehicles. It's also why front brake pads wear out faster than rear pads. Front rotors are typically larger than rear rotors, and front brake calipers are more robust than rear calipers. The brake system is designed with this weight transfer in mind. Electronic brake force distribution, EBD, integrated into the ABS system on modern cars, continuously adjusts the proportion of braking force between front and rear axles based on the vehicle's loading and deceleration rate. Under light braking, the rear brakes contribute more. Under hard braking, more force is directed to the front where the grip is. This optimization happens invisibly and ensures maximum braking performance in every situation. Understanding weight transfer also explains why loading your car changes its braking behavior. The car with 4 passengers and a full trunk has more mass concentrated rearward than an empty car, which changes the weight distribution during braking and affects stopping distance. Heavy loads in the trunk or bed increase the overall mass the brakes have to decelerate and can extend stopping distance by 10 to 20% or more. If you regularly carry heavy loads, factor this into your following distance and braking approach. The parking brake, also called the emergency brake or e-brake, is a separate braking mechanism that operates independently of the hydraulic system. Its primary function is holding the car stationary when parked, particularly on slopes. Its secondary function is serving as an emergency backup if the hydraulic brake system fails. Traditional parking brakes use a cable-actuated mechanism that applies the rear brakes mechanically, bypassing the hydraulic system entirely, pulling the parking brake lever or pressing the parking brake pedal. Tensions, a cable that activates the rear brake shoes on drum-equipped rears, or a small set of drum-style shoes built inside rear disc brake rotors on disc-equipped rears. Some modern vehicles use an electronically actuated parking brake, a motor-driven caliper that clamps the rear brake pads against the rotors at the push of a button. The parking brake's mechanical independence from the hydraulic system is its most important safety feature. If you experience a total hydraulic brake failure, a burst brake line, a catastrophic master cylinder failure, the parking brake still works because it uses cables or electric motors rather than hydraulic fluid. Applying the parking brake gradually in an emergency can slow and stop the car. It won't stop as quickly as the hydraulic brakes. It only acts on the rear wheels and generates less total force, but it's far better than nothing. Use your parking brake regularly, even on flat ground. Parking brake cables and mechanisms can seize from disuse. If you never engage the parking brake, the cables corrode and the mechanism freezes. Then, when you park on a hill and actually need it, it doesn't work. Regular use keeps the mechanism free and functional. For most daily drivers, the factory brake system is adequate. It's been engineered for the vehicle's weight, intended use, and expected performance envelope. But there are situations where upgrades make sense. Upgraded pads, the easiest and most cost-effective brake upgrade, moving from factory organic pads to a quality ceramic or performance semi-metallic compound, can improve stopping power, reduce fade resistance, and, in the case of ceramic, reduce brake dust. For aggressive daily driving or light track use, a performance street pad from brands like StopTech, EBC, Hawk, or Akabono can meaningfully improve braking confidence for $80 to $200 per axle. Upgraded fluid. Factory brake fluid typically has a dry boiling point of around 400 to 450 degrees Fahrenheit. Performance brake fluid, .4 or .5.1, can have dry boiling points of 500 to 600 degrees or higher. For anyone doing track days, mountain driving, or towing in hilly terrain, high-performance brake fluid is cheap insurance against fluid fade. A bottle costs $15 to $30, and the fluid change takes 30 minutes. Upgraded rotors. Slotted or drilled rotors are popular aesthetic upgrades, but their performance benefit on the street is minimal. Slots help sweep away gas and debris from the pad surface during hard braking, a real benefit on the track. Drilled holes help with initial wet weather bite by giving water a path off the rotor surface. But for daily driving, a quality blank rotor from a reputable manufacturer performs virtually identically to a slotted or drilled rotor. Save the money unless you're tracking the car. Stainless steel brake lines. Factory brake lines are rubber, which expands slightly under high hydraulic pressure. This expansion absorbs some of the pedal force before it reaches the caliper, creating a slightly softer pedal feel. Stainless steel braided brake lines don't expand, resulting in a firmer, more direct pedal feel. The improvement in actual stopping distance is minimal, but the improvement in pedal feedback and confidence can be significant for performance driving. They cost $100 to $250 per set. Big brake kits, larger rotors, and multi-piston calipers. The full Big Brake Kit, BBK, is a significant investment, distant $500 to $5,000 or more, that increases thermal capacity, improves heat dissipation, and provides stronger, more consistent braking force. BBKs are primarily a track and high-performance upgrade. For daily driving, they're overkill. But if you track your car regularly, tow heavy loads in mountainous terrain, or have significantly increased the car's power output through modifications, a BBK can be a worthwhile safety investment. Electric and hybrid vehicles add another braking method that's fundamentally different from friction braking: regenerative braking. When you lift off the accelerator in an EV, the electric motor reverses its function. Instead of converting electrical energy into rotational motion, it converts rotational motion back into electrical energy. This reversal creates resistance that slows the car, and the recovered energy is fed back into the battery. The car slows down while simultaneously recharging. Regenerative braking handles a significant portion of daily braking demands. In normal driving, decelerating for traffic, coasting to a stop sign, slowing for a turn, regenerative braking can do most or all of the work without the friction brakes ever engaging. Some EVs offer one-pedal driving mode, where lifting off the accelerator provides enough regenerative braking to bring the car to a complete stop without touching the brake pedal. This has a direct and positive effect on friction brake longevity. EV owners frequently report brake pads lasting 100,000 miles or more because the friction brakes are used so infrequently. The regenerative system handles the vast majority of deceleration, and the friction brakes serve primarily as a supplement during hard braking or as the final stop-and-hold mechanism at very low speeds where regenerative braking is less effective. However, regenerative braking creates a unique maintenance consideration because the friction brakes are used so rarely. The rotors can develop surface corrosion from sitting unused in wet conditions. EV owners in humid or rainy climates may notice light rust on their rotors and hear a brief scraping sound when the friction brakes do engage. This is generally cosmetic and clears after a few brake applications, but in severe cases, the corrosion can pit the rotor surface and require premature replacement despite minimal friction use. Some EV manufacturers recommend periodic deliberate use of the friction brakes to keep the rotors clean. Visual inspection. On many vehicles, you can see the brake pads through the wheel spokes without removing the wheel. If the pad material looks thin, less than a quarter inch, it's time for closer inspection. Rotors should be replaced when they're worn below their minimum thickness specification, stamped on the rotor, when they're warped beyond resurfacing tolerance, or when they've been grooved by metal-on-metal contact from worn pads. Rotors can sometimes be resurfaced, machined to a smooth, flat surface if they have enough material remaining, but resurfacing removes material and brings them closer to their minimum thickness. So it's usually only worth doing if the rotors have significant remaining life. Braking converts kinetic energy into heat through friction. Stopping distance increases with the square of speed. Doubling speed quadruples the distance. Disc brakes use pads squeezing rotors and calipers actuated by hydraulic fluid. Drum brakes use shoes expanding inside a spinning drum. Simpler but worse at heat dissipation. Brake pad compounds include organic, quiet, fast-wearing, semi-metallic, durable, noisy, and ceramic, balanced, low dust. ABS prevents wheel lockup by modulating brake pressure per wheel many times per second. Press and hold, don't pump. Brake fade comes from overheated pads, outgassing, or boiled fluid, spongy pedal. Use engine braking on descents. Morning squeal from rotor rust is normal. Persistent squeal may be compound vibration or glazing. Where indicator squeal means pads are nearly gone. Grinding means pads are gone and rotors are being damaged. Fix immediately. Replace pads at 3 to 4 mm thickness. Replace brake fluid every 2 to 3 years. Your brakes are 4 friction patches and a hydraulic system standing between highway speed and a full stop. They work silently and reliably for tens of thousands of miles, absorbing enormous amounts of energy, converting motion to heat and keeping you alive without acknowledgement or attention until they start talking to you. Squealing, grinding, pulsating, changing feel. And when they do, they're not being difficult, they're communicating. They're telling you that the friction material is wearing thin, the fluid is aging, or the system needs attention. Listen, the brakes are the only part of your car whose sole job is keeping you alive. Everything else moves you forward. The brakes bring you back. Respect them, maintain them, and when they tell you something, whether through noise, feel, or performance, don't ignore the message. If this video finally explained why your brakes squeak, what ABS feels like, or when you actually need to replace your pads, hit like. Drop how many miles are on your current brake pads in the comments so we can see who's living on borrowed friction, and subscribe so you stop ignoring the only part of your car that exists purely to save your life. Later.